Okay. So, hello everyone. Welcome to the afternoon session. Our first speaker is Benoît Doucot from the Laboratory for Theoretical and High Energy Physics at CNRS. So we have 40 minutes.
Okay. Yes. Thank you very much. Yeah, thank you very much. So I would like to thank Subhro and Sergej for putting together this very nice workshop. It's a pleasure for me to be here and to meet you, sometimes for the first time. So I'm going to discuss a work which has a strong connection with the lectures by Julien. Well, that's hardly a coincidence because it happens that we've been working together on this project. And the idea is to really try to show concretely an instance of what Julien told us about how, in particular, in some very explicit models, those ideas from fusion categories can help us to understand the structure of the quantum Hilbert space of a very explicit model. So what I must say, what type of model we are going to use? Well, there have been so far many discussions about the toric code, and deservedly so. It's really one of the most instructive model to understand what topological order can be. But I think it's fair to say that the whole subject was to a large extent launched by Alexei Kitaev in this incredible paper, fault-tolerant quantum computations by anyons. And well, of course, the toric code was presented there, but far-reaching generalizations using basically arbitrary symmetry group, not just Z2 group. And in particular, all finite non-abelian groups are allowed. And it was soon realized that this going non-abelian has a considerable computational power. So I was very impressed by these papers, which appear more now than 20 years ago, explaining that, well, I'll come to that, but in a lattice gauge theory, you have two types of excitations, flux-like excitations around inside plaquettes and charge-like excitations on vertices. But when the group is non-abelian, if you carry these braiding processes, so each of those flux carries a group element. When you make this exchange, the element that goes into, well, one of the two gets conjugated by the other. So in fact, G goes into G if the group is abelian, but if the group is non-abelian, it changes. And it was shown that this transmutation under a braiding event gives rise to huge computational power. So that was an interesting motivation for us. And together with Julien and Lev Yoffé, actually, we proposed that's a Josephson junction array. So you have to imagine that each vertex is a little superconducting island. The black crosses or junctions between those islands. Everything is superconducting. It has to be put in the right magnetic field. And we've shown that this device can implement the realization of the Kitaev gauge model with the group S3. Needless to say, this has never been implemented in real life. Only the Z2 version was implemented, in particular by Misha Gershenson at Rutgers University. And he obtained really very interesting results. In particular, he has shown that doing this creates some sort of qubits that have some kind of protection from decoherence compared to the qubit you can make with just one superconducting junction. So that was the physical motivation. Now I have to, connect to the subject of topological field theory. So actually, I'm not going to use category theory as an input in the model today. I will really start with the gauge theory model. But it's true that when I observed this subject at that time, I was sort of aware that there were some mathematics going on. I remember I had a colleague at LPTHE, Christoph Schweigert, who is one of the experts in those TQFTs. So he was telling us something about these beautiful constructions, but for me, that was really a piece of beautiful mathematics. And as a quant physicist, there was absolutely no reason to pay attention to this seriously, just for the pleasure of the aesthetics, basically. So this construction start basically, the earliest construction started by recitation Turayev started with a modular tensor category, and it defined from this a Hilbert space, quantum Hilbert space on any closed surface. And if you imagine time evolution, quantum evolution, so now your surface evolves in time, so you have a three-dimensional space-time manifold, and you can construct the evolution operator in a sort of purely topological manner. And this is definitely a non-local construction. It uses a surgery of manifolds. Later on, there were some more local construction, the so-called Turayev-Viro construction, which started with a fusion category. So now you know what it is thanks to Julien. And the construction was local. It involved discretized path integral. And there was a very interesting result linking the first construction, the second construction, the local one with the input category A, with the first one, the non-local one, with the category Z of A, which is the Drinfeld center of A. So I'm going to talk later about Drinfeld centers, but in the context of the categories that play a role in the quantum double model. And then I think it's fair to say that enormous change happened, well, after, of course, the Kitaev seminal paper, but this whole zoo, if I may say, of categories appeared in the kitchen of condensed matter physicists, thanks to the stringnet construction of Levin-Wen, because they wrote all these things in terms of a lattice Hamiltonian, the sum of mutually commuting projector, which was a far-reaching generalization of Kitaev's lattice gauge theory model of anyons. So that's the sort of short sketch of the history of the subject. Now there were, of course, very interesting works exploring the connections between the Kitaev construction and the stringnet models. And I think one of the important developments in the field was Julien's exact complete enumeration of the states in those stringnet models. And he got an explicit formula for the partition function, which was based on this Morse-Seiberg banks on the formula on the TQFT side that he could completely match with the lattice model enumeration of the states. So that was a very precise one-to-one correspondence. Now, the problem is that if you want to study the Kitaev quantum double model and do it at the stringnet, you can get only one subset of the excitations. For example, if you want to capture the plaquette excitations, you will like to enforce the vertex constraints exactly. So you're going to enforce gauge invariance, or in other words, you want to impose that you have no charges. You want to satisfy Gauss law, basically. So you're going to work with a stringnet in the category of the representations of the group G. rep G is really what controls the possible charges in your theory. If you're interested in vertex excitations, that is charges, you're going to remove the fluxes. So you're going to impose a sharp fluxless constraint in each plaquettes. Therefore, you're going to work with the fusion rules of the vec G category. And actually, it turns out that these two are Morita equivalent. They have the same Drinfeld center. And it's no surprise that when the outcome of those calculations is that the counting formulae for the states will involve the Drinfeld center of both rep G and vec G because that's the same category. So, well, that's, yeah.
If I construct the 11-man model for either of these, I get all the.
No, you get only one set of excitation, one subset of excitations. That's the thing it's a bit annoying because in the Levin-Wen model, you have a dissymmetry between sites and plaquettes. At the sites, you impose the fusion rule tightly, whereas you have a sort of energetic penalty for fluxes but you're perfectly allowed to create non-trivial fluxes. Then by duality, by going to the dual lattice, you can replace the sites and the plaquettes. So in some sense, the plaquettes of the initial model can be regarded as sites. And then if you want to impose the fusion rule of the dual category, you're going to get only the charge excitations. Okay, we should discuss. I think if I'm thinking about the original version of Levin-Wen models, you definitely have a sharp constraint at the vertices. You really have to implement fusion rules at vertices. For me, otherwise you may have some generalization where you relax. You can use some auxiliary sites to account for the charge excitations, but I think these are not the historical versions of the Levin-Wen models. But I think we should discuss afterwards because, yeah, so these are I flashed the result for the partition function. So you recognize the formula that was written earlier by Julien. You have some vertex and plaquettes excitations. You have some of the objects in the Drinfeld center. You recognize the S matrix and the genus here that appears. And in the thermodynamic limit, we can show that there is no phase transition, no finite temperature transition, consistent with the idea that at any finite temperature, you have a finite correlation length and there's no topological order at finite temperature. So I must say, from the physics standpoint, of course, it's a sort of free onion gas. But I think why is the problem non-trivial and interesting? I think the problem is very interesting from many aspects that becomes clear if we look at the gauge theory description. So the ingredients are, you have a finite gauge group, a lattice, any lattice in 2D. The configuration space is described in terms of for each bond, you choose a group element that I call Jij, I and J are sites, and the links have to be oriented. That is, we have the constraint that if you go this way and that way, you take the product of J12, J21, it has to be the neutral element of the group. Now you pick a potential energy, which is a functional of those group element assignments to bonds, and we require it to be gauge invariant. So what is gauge invariance in this setting? It means the following. You can pick, it's a local symmetry, which means that at a given site, you're free to pick any group element H sub I, and then you get the transformed configuration by using this formula. So note actually the fact that here, if the bond is oriented like this, for G12, you multiply by H1 on the left and H2 minus 1 on the right. And in fact, it's sort of clear that this set of gauge transformations form a group, and this group is acting on the set of configurations. Of course, we want the energy to be gauge invariant, so it's interesting to look at quantities which are only mildly affected by gauge transformation. Well, we know the answer in abelian case. It's simply taking Wilson loops or fluxes around closed paths. They are gauge invariant. The situation is a bit more complicated in a non-abelian case, because if you take a plaquette like this, starting at 0, when you apply a gauge transformation, the flux gets conjugated by H0. So again, if the group is abelian, you don't change the flux. If the group is non-abelian, this new flux can be different. It's usually different, but it remains in what is called the conjugacy class of the group element phi p. So now you have a very simple recipe to write down gauge invariant in potential energy. You take a function that depends only on conjugacy classes of fluxes. And so that's the recipe. And the recipe for the simplest situation is to take an additive function. So that's the free N gas, if you wish. It's a sum of plaquette terms. Of course, we could add binary plaquette interactions, but in fact, that's the simplest thing that we can do. So we have a gauge invariant functional energy. And one thing that will play a very important role in the understanding of the structure of the Hilbert space is the so-called gauge orbits, because the essence of gauge theory is that you have a redundancy in your description. So all configurations which are linked by gauge transformation should be some kind of similar quantum state. But what I'm saying is not exactly true, but I will come back to the statement when I discuss the quantum version of the model. But so it's very important to understand what is called the set of gauge orbits. That is, how many families of configurations I have that are related by gauge transformation in one family. So actually, there's a very interesting criterion to decide when two configurations, J and G prime, are in the same gauge orbit. It's if and only if there exists a single H0. So you imagine that you're looking at fluxes with a common origin, so that any closed loop starting and ending at 0 gives rise to conjugated fluxes, and the conjugating element has to be the same for all the loops. Now, of course, this is not very practical to check all possible loops, but it's fortunate that the loops can be sort of decomposed into elementary ones. And it's even much easier if you know in advance that most plaquettes are in their ground state. That is, most plaquettes have no flux. Therefore, what you can do is that if you have, for example, a plaquette like this that has no flux, even if the group is non-abelian, it's a sort of non-abelian version of the Stokes theorem, you can deform the red-blue loop into the blue one, and without changing the flux. So it gives us a much more practical gauge invariant criterion, or to decide whether two configurations are in the same gauge orbit. You have to test basically only from loops that generate what is called the fundamental group of your surface, where you remove a subset of the plaquettes that carry fluxes. So it's simply the translation of this idea that the flux cares only of the homotopic class of the loop. You're allowed to deform your loop as long as you're not crossing a plaquette that carries a flux. So that will be the usual intuition. And I'd like to really spend time on this idea because for me, that illustrates very well. There were questions about what's the meaning of the labels. Do they correspond to precise quantum mechanical states in the underlying hardware model? And I think this point is really illustrated already by the fact that, as we said, if we have one flux, it's characterized by a conjugacy class of the plaquette flux. But this information is not sufficient to determine a gauge orbit for more than one plaquette excitation. So maybe let's go to the example of group S3. S3 is the permutation group of two elements. It has, three elements. It has 6 elements, 6 permutations. You have the the identity permutation. You have the 3 transpositions, and you have the 2 cycles. And I choose generators, 1 transposition, 1 cycle, and you have 3 conjugacy classes. What's going to play an important role are the normalizers of these generators. Normalizer is the set of elements that commutes with a given element. So everybody commutes with the neutral element. So normalizer of E is S3, normalizer of X is EX, and normalizer of Y is EYY squared. So now imagine that you have 2 fluxes, phi1, phi2, and you know that both of them are in the conjugacy class of X. And actually, this corresponds to label in the appropriate quantum double of the categorical description that Julien presented. So I have the same labels, CX, CX. But now, suppose I consider this second configuration of pair of group elements, phi prime 1, phi prime 2, X and YX. YX is also in the conjugacy class of CX, but it's a very easy check to see that there's no common element that allows you to go from phi 1, phi 2 to phi prime 1, phi prime 2 by conjugating with the same element. So, which means that basically phi 1, phi 2, and phi prime 2 are in different gauge orbits, although they correspond to the same pair of conjugacy classes. And you can give lots of examples like this. So it's a very common phenomenon. In other words, for me, that's the prototype of what's going to give rise to a fusion tree. In other words, you have 2 elements that have the same CX, but you can fuse in different channels. So somehow, knowing the labels in terms of labels for objects in the Drinfeld Center doesn't give you enough information to, and still it's really the classical description, the classical description in terms of the gauge orbit. So it means that you have some sort of additional degrees of freedom, non-local, that sit between the 2 fluxes. And for me, that has always been fascinating. But when I tried to struggle with this, I could even write down some algorithm to count the degeneracies, but there was no elegant formula because I didn't know about fusion categories at the time. André, you want to?
Yeah, Benoît. So you know, I'm trying to process what you said on the slide and what you're saying. So, okay, so you made 2 statements. One is that the M particles of the fluxes are labeled by the conjugacy classes.
Yeah.
Right. So naively, I would think that that's enough, you know, to characterize excitations. But here you're saying that
it's okay for one excitation, but not for a pair of excitations.
I see. So if you have a pair of fluxes, like you have example there, like XX and XYX, even though that in some sense the same conjugacy class,
yeah,
you're saying what, you cannot annihilate the 2 of them?
Yeah,
or you can, or
Okay, that's a very good question. I don't know exactly how to analyze actually these examples. I think suggest that you have something like fusion trees that take place, but to really assign a fusion tree to this class and that class, I'm not sure I know how to do that. But if you're interested, I'd be very happy to discuss further, because I think to give a sort of outline, we get the right counting, but the one-to-one assignment between fusion trees and quantum states described in this very explicit and pedestrian way, I don't really know how to do it. The counting is perfectly fine, but the state assignment remains a bit mysterious, at least to me. So if anybody is interested in sorting out this question, I think I'd be happy to discuss further. Yes, thanks, Andre. So, yeah, yeah. Well, it's just that they belong to a given different gauge orbit. So there's no way they can be related by a gauge transformation. So there's no way, even if you impose the Gauss law at the quantum level, there's no way they can form the same quantum state, basically. Although they have the same labels. Yeah, so that's, okay, that's very, the reason is that to conjugate from x to x, you have to use the normalizer of x. To conjugate from x to yx, you need actually y squared times the normalizer of x. And these two states have a vanishing intersection. So, yeah, so that's very, so they really, in other words, quantum mechanically, they would, if I project on a singlet sector, they will give rise to orthogonal quantum states. That's what connects them. That's still, I think that's the reason why fusion trees were invented, because there's a sort of non-locality that is involved. And it seems that the way that was invented to handle properly this form of non-locality was through the technology of fusion trees. But I agree that it would be nice to have a much more one-to-one translation between fusion trees and quantum states. And I just say that the numbers match numbers of fusion trees, number of quantum states. But yeah, so I realize that I'm almost done, but I haven't yet started even to discuss the quantum theory, but that's fine. I'll be here for 1 more week, so at least we can find time to discuss further. So this notion of gauge orbits, actually, it's, I like those considerations because it shows that gauge theories has a very strong topological flavor. I've shown you that you can deform path as soon as you move along fluxless regions. And for example, imagine that you're on a sphere. So I imagine, take the plane plus 1 point at infinity, and I punch F holes, F for fluxes. I put some fluxes G1, G2, Gf on those holes, but I told you the rule is to relate all those fluxes to a common origin. So the correct fluxes, you know, involve the conjugacy by this path K1, K2, Kf. Each carry a group element. And on the sphere, you see this orange path gamma. I imagine that I punch F holes. I can imagine that if O is the North Pole, I can always move gamma around the equator down to the South Pole. So the path gamma is contractible, which means that we have this constraint. The product of fluxes should be the neutral element. So gauge orbits are in one-to-one correspondence with the F apples of group elements subject to the product constraint phi 1, phi 2, phi f is equal to the E, neutral element, modulo the equivalence relation that this F apple are conjugated by a common element H0. So, and actually, Julien has done this on a computer. You can really enumerate those orbits very efficiently, but you don't get that way obvious, elegant formulae to do the counting of the orbits. So that was my problem 20 years ago, but I knew nothing about fusion categories again. So you can also work out these gauge orbits on a genus G surface with F holes. So another description of, for example, this is genus 2. You take this octagon, and the idea is that each corners have to be identified with this point O, and then you add handles. So, for example, this path, this closed loop here, it's a kind of Aharonov-Bohm flux that has to be identified, this one with a reverse orientation. Well, okay, that's something relatively standard, but I'm afraid I won't have time to say more. Just the idea that you account for the non-contractible cycles. There are 2G cycles of that sort, pi A, pi B, or 1 to G, by those Aharonov-Bohm fluxes. And this time you have the constraint, and again, the same equivalence relation. So that's the classical gauge theory. The space of classical configuration breaks into those gauge orbits that can be efficiently sampled using this algorithm. But now we want to do quantum mechanics. After all, that's what we like in this game. So quantum mechanically, as Frank rightly pointed out at several times, we need the Hilbert space. So what's the Hilbert space? We have orthonormal bases formed by kets, which are labeled by these gauge configurations. So the potential energy function becomes a diagonal operator in these bases. Now, I told you about gauge transformations. Those are definitely non-diagonal, and with this choice of orthonormal bases, gauge transformations are clearly unitary operators. And the kinetic energy term, to make life interesting, has to be off-diagonal, of course. But to make it even more interesting, it has to commute with all these gauge operators, and also to preserve the conjugacy classes of plaquette fluxes, because we want also the potential energy, yes, to be gauge invariant. So that condition is built in by the choice of the diagonal operator that is commented yesterday. But the way to achieve a non-diagonal term that commutes with the gauge transformation is simply at each site to introduce some projectors on the various irreducible representations of the group G. So I hope that most of you are familiar with this idea. If you have a group G, it has irreducible representations. And if you know what is called the characters of the irreducible representation, that is the trace of the operator that represents the group element, you can build the projectors. And what is nice is that by construction, they commute with all the local gauge generators. So, and in the spirit of the Kitaev model, you give positive energy penalty whenever the representation is not the trivial representation. So in some sense, well, I think in the original model, Kitaev set this 0 if it's a trivial representation, and finite value for anything which is not the trivial representation. But I think it's a bit annoying because there will be additional degeneracies, and to understand the structure of the Hilbert space, it's better to lift all those sort of non-essential degeneracies. So I think I insist that the A's should be made different to lift the, likewise, we want to lift the degeneracy between different conjugacy classes for the fluxes. So that's slight generalization compared to the Kitaev model. So the construction of energy eigenspaces, actually there's a very nice paper by Komar and Lando Cardinal. So That's my sort of translation of their paper. Perhaps they use slightly different language notation, but I think the idea is the same. Consider the set of gauge orbits defined by specifying conjugacy classes of placket fluxes. So phi I belongs to the conjugacy class of xi. The corresponding classical configurations span a degenerate subspace for the potential energy operator. That's just a gauge orbit, but that is also stable under gauge transformations. So in fact, when you go quantum mechanically, what happens is that you have a stable subspace for the symmetry operation. The Hamiltonian acts in that subspace and commutes with the gauge transformation. So the energy eigenspaces can be obtained by decomposing this invariant subspace associated to one set of orbits, basically, into irreducible representations of the gauge group. Now, actually, since the group acts independently at every point, the irreps of the full gauge group are specified by collections of irreps at each vertex. So physically, choosing an irrep means choosing at a site, choosing a type of a charge, non-abelian charge at that site. And we are going to consider those irreps where only a finite number C of charges of those irreps are non-trivial. So the key idea now is to compute the multiplicity of that representation, particular representation, on the Hilbert space that is attached to the orbits that have the specified conjugacy classes of the different placket fluxes. And you see, as I said before, there could be many different orbits. So we obtain a degenerate energy eigenspace. So the energy is given, it's easy, there's no work to diagonalize it. You have the potential energy that depends on the conjugacy classes, and the sum of the energy attached to the various charges. That's why I'm saying it's sort of free anion gas. And the punchline is that the multiplicity, the dimension basically of this degenerate energy eigenspace is a product of two factors. There's one that depends explicitly on everything, conjugacy classes and charges, and it will be computed actually using the formula that the banks, Moore-Seiberg formula that Julien gave us, using the Drinfeld center of Vecchi category. And then there's a sort of group theoretical factor, which is the product of the dimensions of the irreps. So this is definitely not in the topological TQFT theory. It's additional degeneracy, but this one is. So I realize I have 0 minute to explain what we did in the end. But yeah, so, okay, so perhaps I should flash at least the important formula. The important formula. Yeah, so I wanted to tell you about categories, but that will be more informal description. So that was my description of the Z-Vecchi category. But again, please ask me during the breaks. And yeah, so the punchline was that this multiplicity, yeah, the beautiful formula is this one. So on the sphere, you know, these objects, these conjugacy classes and representations are promoted into objects in the Drinfeld center category Z-Vecchi. And in fact, one of the questions that Frank kept asking was, where is the Hilbert space? So in category theory, natural Hilbert spaces do not lie in objects, but in what is called the arrows between the objects. So in fact, it turns out that our multiplicity can be reinterpreted as a, so this, by this is meant the number of arrows between the vacuum And this object that is this tensor product in Z vec G, this has a finite dimensionality that can be computed by the technology of fusion trees that Julien explained. And also, one thing that I was very happy with is that Julien had many questions when it came to gluing. And in fact, we can do the gluing explicitly in this setup. So taking into account of the extra degrees of freedom due to the Aharonov-Bohm cycles around the handles can be done. It's slightly more fancy, but it's relatively simple group theory. And what you get actually, it's exactly as in Julien's formula this morning. You have objects that code the plaquette excitations, the charge excitations. Now come the handles, the genus part. What you have to do is to consider all possible objects in the Drinfeld center. So actually I remembered something before that objects are represented by conjugacy classes and E-reps of the normalizer of the corresponding element in the conjugacy classes. And what happens is that for each handle, you have a pair of the object of the dual object. You take the tensor product of all this, and again, your multiplicity basically is given in terms of the dimensionality of a space of arrows that can be computed by the technology of fusion trees. So, so for example, when you sum over all possible orbits, the formula is that you have, again, this object that codes the fluxes, the charges, and for the higher genus, you take all the tensor product of all possible simple objects in the Drinfeld center together with their dual object. So I'm done. You know everything now because of Julien's lecture. So that's how we got this global multiplicity formula. So I think what is left to do, I think it shows really the validity of the counting as defined by the rule of TQFT. But there are several surprises still due to the lattice. The fact that only this type of objects appear in the Drinfeld center. These are not the most generic objects, either the pure fluxes or pure charges. The more complex objects appear at finite genus, and when you want to compute all the possible fusion channels. And I think what would be nice would be to try to go beyond this sort of counting formulae to make a sort of direct dictionary between the fusion trees and the actual copies of the various irreducible representations that corresponds to the various multiplets. And one last thing that maybe this work could suggest, as you heard, is that there are twisted versions of these quantum double models. And one actually intellectual challenge for us is that physically, when you twist with co-cycles of the gauge group, you have flux that you have Chern-Simons means attaching fluxes to charges. So you're going to have flux bound to local charge excitations. And it reflects that the gauge group now has some projective representations. So maybe it would be interesting because there's a theory for those twisted Drinfeld centers, whether the precise counting will still hold in this twisted case remains to be seen. So, okay, I'm sorry that I could not provide much of the detail that I advertised, but I hope at least what I said was not too confusing. Thank you very much.
So questions?
Yeah.
Each coupling constant is different for each side.
No, it's okay. We could also put disorder. That would be absolutely no problem because it's a sum of local terms. No, I just want to be sure that the energy multiplets that I'm considering are the smallest possible ones. Because I told you the formula for the energy, for example, is additive in the various A's that correspond to the different charges that you put in your lattice. So suppose all the A's are the same. Well, of course, it will give a lot more degeneracies than what you expect in the generic case. So I want to sort of be sure that energy multiplets have the smallest possible size. That's that's the main reason for doing this. Yes, okay.
Yeah, I have a related question to this degeneracy. So are these degeneracies topological in a sense of?
Yeah, I think these ones are complete. This piece is topological. You see, as soon as you have this these objects, well, that's, you may say it's a number of fusion trees, or these things are completely topological because you know nothing about the lattice, the model. It doesn't care whether it's a trivalent, random lattice. It cares only about the genus of the surface and the modular tensor category, that is the Greenfeld center of the group. So this piece is totally topological. And then if you are on the lattice, you have this extra, with the gauge theory implementation, you have this extra group theoretical multiplicity. And I think that was part of the difficulty when we started doing this. I remember that we had many discussions on what because of course we tried, I think, to check with the purely topological formula, and it's clear that we had more degeneracies that had a non-topological origin. So finally, we understood, we managed to disentangle the two sources of degeneracies. So which shows actually that when you have a particular lattice implementation, there might be some additional degrees of freedom that may not be totally described by the TQFT itself. And it's not totally clear to me what type of physics we can have.
Because it sounds that it's related to charges only. Right?
Oh yeah, charges only, you're right. Yeah.
To their size of the reps.
Exactly. So it's related to the well-known fact that when you have the so-called regular representation of the group, that is, if you have a vector space that is labeled basis vector by group elements, its dimension is dimension of the group, and each irrep appears with a multiplicity equals to its dimension. So I think that's precisely this phenomenon that appears. And I think that can be seen in a string net version of the model. Because when you try to map the model on the string net, if you use the RepG's string net, will probably have these multiplicities that will appear, I suspect.
So can one say that it's related to some extra symmetry in the model which you have compared to, like, there is something which comes from topology, which is maybe related to this higher form symmetries, but maybe there is some extra symmetries which are rise to extra.
You're right. I don't think we have, at least I don't feel I have a full understanding of the physical interpretation of those additional local degrees of freedom. Yeah, thank you. You're welcome.
Okay, so I don't see any other hands. So maybe we thank Benoît again.
Thank you.
Some product state. So there's nothing topological about it whatsoever. Completely boring trivial phase. In fact, if you look at the symmetry class, I allow all perturbations. So if I look at the symmetry class, this belongs to class A. So indeed, if you look at the classification, it has only the trivial phase. But why I say this is the second most boring phase diagram as opposed to the most boring phase diagram is this point in between, just represented by an asterisk. It is obtained by setting both the staggered hopping amplitude and chemical potential to 0. When we have an ordinary tight binding model at half filling, so we have a gapless state. It's destabilized by either bond dimerization or staggered chemical potential. Now, why is this interesting? I'll demonstrate why the states are interesting in 3 different ways. The first, I'll go to the periphery of the phase diagram and then just look at what happens in form of a movie. So let's go to large positive chemical potentials. The chemical potential when because of the nature of this term, you only tend to occupy every odd sites. You have fermions on sites 1, 3, 5, and so on. Let's go all the way here. The site, let's track this fermions on site number 1. It now becomes delocalized on a dimer between sites 1 and 2. If you go to j goes to minus infinity, it's now it prefers occupancy on even sites. So this fermion which started on site 1 went between sites 1 and 2, now goes to site number 2. If I come here, it goes between sites 2 and 3. And when I come all the way back, the fermion finds itself in site number 3. So as I go all the way around the periphery of the phase diagram, the charge is transported by precisely 1 unit cell, which is why it's called a charge, Thouless charge pump. Yeah, so that's the family of states at the periphery. I can't hear.
At Hamiltonian, how are you defining the infinity for J? It is,
How am I defining infinity for J?
so J is the multiplicity of that second term, na? So how at the infinity is coming? I'm not able to understand.
It's a tuning parameter. So I tune it to infinity to see what happens.
Okay.
Okay, so this model can be analyzed in totality because it's a free fermion non-interacting system. So I can pass on to the band theory, and it's very easy to check that only at the origin the bands cross. Everywhere else the bands are well separated with the chemical potential exactly at 0. So everywhere apart from the origin we have a ordinary single filled band. It's not topological. There's a well-known way in which we diagnose a Thouless charge pump, which is consider any loop in this phase diagram. Okay, there are multiple types of loops, one which can wrap the origin, one which does not have to. In any case, we can define a Berry connection in the usual way. Now, I treat the momentum space, since we are in the single particle framework, I treat both momentum and parameters on equal footing. So I can define a connection on both momentum and parameter space. So I use this symbol psi to represent the collective coordinates representing both momentum and the parameters. So once we define this, we can take the Berry connection and define the first Chern number. So the first Chern number is something that can be integrated over any 2-dimensional surface. And I can consider integrating over a torus formed by any of the loops. Just take any parametric loop and the momentum space. So in this 2 torus spanned by a loop and momentum, I can integrate the first Chern number. And then it's easy to check that if the circle wraps the origin, we have a non-trivial pump, and then the Chern number takes integer values, in this case 1. On the other hand, if we consider any contractible loop, right, the Chern number vanishes and we get 0. So the Chern number is quantized. So it's a quantized invariant that tells you whether there are non-contractible loops. So this puncture over here in the middle is representative of the non-contractible nature of the space of matter. All this is well known fairly, but we can do something better. We can just consider, instead of computing the Chern number at each point in parameter space, we can compute using the Berry connection. We can just integrate the Berry connection over just the momentum direction over the S1. The standard way of computing the Berry phase. And if we consider the Berry phase at each point and just plot it for every parameter value, we notice something very familiar come about. So this of course, everybody would recognize is the topological texture of a vortex. And this generically is what happens when the system, the parameter space that we're considering has non-trivial topology. In fact, at this point, we can let go of all our assumptions. We don't need translation invariance or free fermions. the Berry phase computed by integrating the Berry connection over the momentum direction, just over the middle one, for each point in parameters. Sorry, say it again. Yeah. One point in J and delta. I integrate over K. So I get a U1 well-defined angular variable for each point, and I can represent the angular variable using the angles of an arrowhead. Precisely. So as was pointed out, this can also be obtained experimentally, for example, by measuring the polarization. And one does not need any assumptions about the system being non-interacting, free, whatever. So this local observable actually points out how the phase diagram has a texture, kind of like surface of a cat or something. Yes. But it's not quantized. So Berry phase does not need to be quantized, and it's not. So it's not, I wouldn't call it a winding number. I'm not sure what you have in mind, but it's certainly not a winding. That's Chern number. You're describing the Chern number. Oh, sorry, I think the expression for the Berry phase got erased. It's not many body, it's the single particle Berry phase. Yeah, it's a single particle invariant, but there is a polarization is the many body observer. Oh yes. I'm going to stay. All of this is well defined only in the gap phase when there's one single field.
Here the plotting that a Berry phase is like plotting a vector, right? In the delta and J direction. It's you're
plotting an angle for each point in.
So if we plot a vector like in the I cap direction and J cap direction for any like electric field, we get a similar kind of structure.
I'm not plotting a vector, I'm just plotting an angle at each point.
Okay.
With using an arrowhead. So it's not a vector really, but it's kind of like what is this in an XY model? That's the closest analogy.
But Berry phase is vector in the K space, right? Vector potential in the K space.
No, we should talk later.
Okay.
Okay. So correct. That's right. So this is like a different way of looking at it. So let me move on to the second way of looking at the same thing, or the third way of looking at the same thing, which is we can just study the theory on open boundary conditions. So it turns out that when we study the theory on open boundary conditions, there's exactly one line where we have the system as edge modes. By edge modes, I mean zero energy edge modes, boundary zero modes. And it happens in a very particular way. It's a one-dimensional line in parameter space. It's actually a codimension one line, which terminates on this bulk gap closing point. And this is a particular feature which you cannot remove. So I claim that you can actually compute the whole thing is exactly solvable. So we can look at the correlation length of how well localized the edge mode, the boundary zero mode is, and there's an expression for it over here. So at the periphery, it's very well localized to the edge, but at the center, it delocalizes and becomes part of the bulk spectrum, bulk gap closing spectrum. And this is the manifestation of bulk boundary correspondence, if you will. Yes. So these broken lines are the locations where you see the zero energy boundary. In fact, a very careful observer would understand why this is happening immediately. If you tune J equal to 0, the staggered chemical potential, what you get is precisely the sushi for Heeger model. So this actually seems like an accidental feature. Like, I tune J to 0, I have the sushi for Heeger model. Sure, there are edge modes. In fact, it's not. So the anomaly that appears here is a special kind of anomaly. It goes by the name of anomaly in the space of coupling constants. And the easiest way, in my opinion, to demonstrate this is take the same model and add a finite chemical potential. So the effect of that is the gapless point blows up to form a gapless phase. There's a stable region where you have a gapless metallic phase, one-dimensional metallic phase. What happens to the edge modes is very curious. The red and the blue lines now represent edge modes on the left and the right end of the chain. So in this parameter regime, the system has edge modes only on one of the ends but not the other. Whereas on the blue line, the system has edge modes only on the right end. So this kind of a phenomenon does not happen for ordinary topological phases. So this boundary phenomenon is some kind of a global thing that occurs in phase diagrams due to the presence of non-contractible loops. It's not associated with any topological phase of matter. In fact, in the presence of chemical potential, there are no symmetry classes that have SPT phases, and none of these things are SPT phenomena. Okay? So we call these estranged edge modes because the name.
Could you explain again what happened over there?
Sorry, say again?
Can you explain again what happened over there?
So if you look at where the left edge modes lie.
I mean, what is the physical parameter change in your system so that from one point to this?
Oh, chemical potential. Ordinary chemical potential. I change the filling number. That's it. So I start partially populating one of the bands.
Sorry, I missed. Like, so do you think about it as some kind of SPT or not?
It's not. So this slide is meant to prove that it's not an SPT. Having edge modes on only one end but not the other doesn't happen for SPT.
Yeah, like not the ordinary one, but like there is some robustness still.
Yes, yes. So the robustness I claim is not coming from accidental SPTs, but the fact that I'm going around this in a non-contractible loop. Is a bulk boundary correspondence corresponding with that phenomenon.
So then what kind of phase of matter is?
It's a trivial phase of matter in the usual sense, but it has non-trivial phase over a circle, if you like that kind of a terminology. I'm borrowing this from Hermely, but it just has non-contractible loops, is what I'm saying.
So it's not protected by symmetry?
It is protected by U1 conservation, nothing else.
It's protected.
By U1, just
U1.
charge conservation.
But it's not an SPT, although
not
it
an
has edge modes.
That's
on
right.
This, like, on that line. Right?
That's right. SPT would require edge modes to be there for all parameters. So clearly it's not an SPT.
No, but imagine I just like fine tune to this line.
Right.
So should I think about it as I do not follow the logic. So that's kind of.
So along that line,
yeah,
you'll start as a person doing an experiment. You'll find the system without edge modes, phase transition at a critical point,
yeah,
and then state with edge modes.
yeah.
But the edge modes are on just one end.
You mean on this picture, right? When
No,
you
no.
go on.
So this picture represents the red line,
Yeah,
represents edge modes occurring only on the left end of the chain,
right.
physical left end of the chain. I might have my lefts and rights mixed, but only one of the ends of the chain. Just parameters, how the model, the details of the model. Sure, but the open boundary conditions change that because it's not symmetric because it's like, on one end there's like even occupancy, on the other end there's odd occupancy, so it breaks that symmetry.
We should, you had mentioned this, but forgotten. How important is the fact that the 0, point has translation of?
It's completely unimportant. We can see this, I mean, not straightforward, but using Bosonization, we can show that it's not important. For example, in the presence of interactions, you can break translation invariance. It's fine.
By this unit translation invariance?
Yeah, it can be broken. Okay. So, like I said, the translations are not important at all. The only symmetry that's important is U1. So the question is confusing because with periodic boundary conditions, there is no anomaly. The anomaly only occurs on the boundary. The system is not anomalous. The boundaries are anomalous. Like SPT phases, it's just the boundaries that are anomalous. That's right. So they construct effective theories for just the boundary, for example. That would be anomalous. Okay. So finally, Usually for SPTs, you have edge modes on both edges. So this is, so the appearance of edge modes is connected to something called anomalies in the space of coupling constants. It's not an anomaly for the symmetries, like for SPTs. It's an anomaly between the symmetries. It's a mixed anomaly between the symmetries and the compactness of parameter space. I'm not. We can talk offline. Okay. So the whole thing can be understood very nicely using field theory. So the parameter for the system near the origin, we can consider an effective theory which is ordinary 1 plus 1 dimensional Dirac fermion, and the two coupling constants correspond to the two masses. If you remember Ashok's lectures, one of them is an ordinary mass and the other one is called a chiral mass. So it's precisely a conformal field theory with two relevant deformations. And so it makes sense that to close this gap, you need to tune to precisely two parameters. But what can be done is also we can reorganize the masses into something called the chiral form, the complex form, I'm sorry. Where it becomes very clear that under renormalization group, there are two constants. One is the radial direction, delta square plus j squared, and the angular direction, which is arctan of j over delta. Under renormalization group, both the mass terms have the exact same operator scaling dimensions. So only one of the parameters renormalizes. So m becomes very large, whereas the angular component does not renormalize. So in fact, it represents a moduli space of fixed points, which is precisely the shape of a circle, telling you that there are non-contractible circles in this space. We usually used to thinking about fixed points as points, but the correct way of thinking about it is like there's a manifold of fixed points which has some non-trivial topology, and that once again tell us the shape of the phase of matter. And in fact, if we just plot alpha, which is what the theory renormalizes to, you once again get the same vortex at the origin analytically as you do by plotting the Berry phase. Although we don't really have a connection between these two quantities, field theory and the Berry. Both. The fixed point is the basin of attraction. There's no point. It's a fixed. So the basin of attraction forms a fixed manifold. That's a circle. So the entire phase flows to one point on the circle. Each point in the phase flows to one point on the circle. Okay. So finally, we can introduce interactions, and this is my interest. The gapless point actually under strong interaction splits up into a terminating first order transition, and we have a conjecture that all these terminating transitions can be interpreted as obstructions that appear in the middle of a non-contactable cycle such as charge pumps. Okay, so I'm very short on time, so I'll move on to I summarize and then move on to the final part of the talk. So there is non-trivial topology in the Rice-Millie phase diagram that can be detected geometrically using this vortex structure of polarization, and topologically we can compute the Chern number to any loop and momentum direction. And in field theory, we can just reproduce the same result by counting the number of relevant deformations obtained at the core. So I must say that the core of this vortex is called diabolical point by Kapustin and collaborators, and I'll use that terminology. Yeah, I would consider that as a feature, not a bug. So I mean, imagine what can happen for other phases. Yeah. More pragmatically, the same. Okay, a short answer is okay. Let me hold off on that question till the end. I have more to say about it. Okay, so how does it generalize? So for higher dimensions. So I'll begin by pointing out that the reason why all of these things are tractable is that Kitaev has a very interesting theory about the structure of the space of such states. So let me state a few definitions before stating Kitaev's conjecture. So ground states without topological order, like all the wonderful things that we heard in all the previous talks, I'll define them as invertible states. This includes, amongst other things, not just the trivial product state, but also things like quantum Hall, topological insulators, and so on and so forth. So these are called invertible states. So let me, if I have, consider the space of all invertible states in d dimensions with fixed attributes. For example, let's just say that bosons are fermions and whatever symmetric group that you want to consider. So with this fixed attributes, let me call such space as ID. Now, Kitaev conjectured about a little over a decade ago that as a sequence of topological spaces, ID, where D equals 1, 0, 1, 2, 3, and so on, these topological spaces form something called an omega spectrum. And this is determined by precisely one condition, which is if you consider the space in D dimensions, it has the same homotopy, like it has the same topology as the space of loops in D plus 1 dimension. That's what defines an omega spectrum. It's a series of topological spaces where with an index labeled by a number with 1, 2, 3, and so on, integer, such that the space in D dimensions is isomorphic, not isomorphic, is topologically equivalent to the space in D plus 1, the space of loops in D plus 1 dimensions. What is? Oh, no. So what does this tell me? This tells me the consequence of this particular phenomenon is that homotopy groups of the space in D dimensions related to a pi n of ID, what the nth homotopy group of the space of states in D dimensions, is exactly the same as the n plus 1th homotopy group for the higher dimensions. Exactly. So the important thing is pi 0 are nothing but the disconnected components, which are nothing but the phases of matter. So what this is telling you is that distinct phases of matter in D dimensions precisely label loops, non-conductive loops in D plus 1 dimensions. And this is completely clear when you look at charge pumps. Charges are the closest equivalent to a phase in 0 dimensions. And loops are labeled by charges, and hence they're called charge pumps. But more interestingly, you can have pump of charge pumps in 2 dimensions, so on and so forth. Now, okay, all this is nice, but how do we study this physically? So the expectation is that the vortex in 1 dimensions will guarantee that a generic phase diagram in 2 dimensions will have a topological structure of a hedgehog. Right? That's the 2-dimensional texture that one can expect. I should say 2 spatial dimensions. Parameter space has a topological structure of a hedgehog. So how do we see this? Now, this actually, so I should also mention that Kitaev conjectured this a long time ago, but recently there's this paper by Yosuke Kubota, who claims to have a proof of Kitaev's conjecture. For the small world of people who are interested in this, it's kind of a big deal. Anyway, so not only did Kitaev make this conjecture, but he also gave a recipe to construct, given a Hamiltonian family in D dimensions, there's a recipe which these authors have labeled the suspension construction based on some math result of how to construct higher dimensional models. And the result, in words is quite straightforward. You take D-dimensional systems and keep layering them in a particular way that introduces a new spatial dimension and introduce a new coupling constant to couple these, which introduces a new parameter. So new dimension by layering the lower dimensional system and new parameter that introduces the coupling between them. Of course, this has to be done in a particular way. But using this recipe, one can construct from lower dimensional family all kinds of higher dimensional examples. So we can do that precisely to the Rice-Millie model and construct non-trivial examples in higher dimensions, which are supposed to exhibit this texture. So in maths, this is what it looks like. So D-dimensional ascendant, as we call, of the Rice-Millie model can be constructed by layering these models with staggering for a particular reason, and then coupling in sort of a new dimer. This introduces a new parameter. So all of these continue to be free fermions, so we can analyze them completely without any excuse, and it can be pushed in a block form. So the block Hamiltonian has a very nice structure. It's a series of numbers coupled to gamma matrices in many dimensions. Of course, if you are familiar with the fact that K theory is the thing that classifies free fermion systems, the appearance of gamma matrix should be absolutely not surprising, and indeed that's where it comes from. It's a subtle answer. You realize that to be in the right part of the phase diagram to see these textures, there is actually a minimal number of bands, as you'll see soon. If you keep increasing, it's fine. So there can be witness bands as K theory would require, but if you make it too small, then you won't be able to see this. You'll just end up in a part of the phase diagram with nothing, no texture. Indeed, that's exactly why. Okay, so how does one, so I showed this vortex, so how do we get these vortices in higher dimensions? So as Apur was asking, it turns out that for spatial dimensions D, this recipe produces a 2 to the d plus 1 band model, of which half of them are filled. So the number of filled bands are 2 to the d. So as we go in higher and higher dimensions, we get larger and larger number of bands. So for the model, the two-dimensional ascendant, we have 2 filled bands. Sorry, I think there was a typo. D is off by factor 1, so it should be d minus 1. So here you have 2 filled bands for 2 spatial dimensions and 3 parameters. So this is the phase diagram. There are 3 parameters which are labeled as delta x, delta x1, delta x2, and j. Since I just not describe them, but I'm happy to say what these things are later. But it's a free fermion model with 2 filled bands, and in this phase diagram, every point is gapped except at the origin. So to bring out the texture that I promised, what we need to do is take the 2 filled bands, and now we have multiple bands. So the appropriate thing to construct is a non-abelian Berry connection. So I construct a non-abelian Berry connection over, once again, the 2 momentum directions and the parameters. And if I enclose a sphere, I can now define the second Chern number, which is something that one needs to integrate over a 4-dimensional manifold. So the 2 coordinates of the sphere that I've wrapped over here and the 2 momentum direction will precisely give me the 4-dimensional space that I require. So to repeat what I said, construct for this 2-filled 2-band model the non-abelian Berry connection and the second Chern number, and evaluate it over the 4-dimensional manifold obtained by considering the sphere in parameters and the 2 momentum directions. Sorry, what? Corner. I'll come to the boundary soon. Let me just finish this and I will come to the boundary. So if you evaluate the second Chern number, it indeed evaluates to a non-trivial value, telling you that this represents a non-trivial sphere in the 2-dimensional model. But how do we get the geometric quantity, right? The equivalent of polarization. So it's actually quite simple. The polarization originally was related to the Chern number through Stokes' theorem, and one could do the same thing over here. So instead of evaluating for an entire sphere, we can evaluate some kind of a loop. We consider some kind of a loop and any bounding surface and evaluate the integral for the second Chern number. And what we get, as you would guess, is the Chern-Simons form. So this is a non-abelian Berry connection and the Chern-Simons 3 form, which if I integrate over any loop with the 2 momentum direction, will give me a good geometric quantity. And using this geometric quantity, one can actually find out, like, by foliating the system in a particular way, we can bring out this hedgehog texture. So what is this U1 quantity? Like, so this is a quantity that cannot be assigned to every point in parameter space, but for every loop in parameter space. So this is a manifestation of what recently has been studied and goes by the name of higher Berry phase. So I'll say more about that a bit later, but maybe for this. So typically for higher Berry phases, one usually needs to, there's a lot of work that's been done about these higher Berry phases. And for interacting systems, for example, spin chains, it has been known that, I'll finish in a minute. Oh yeah, I have 5 minutes. So it has been known that the appropriate quantity to consider are some very complex mathematical objects called gerbs. Indeed, like, if you look at these papers, they give you a nice way to go take a spin chain and then extract to discover this gerb structure. But it turns out that and bundles such as what we're looking at are not good. But for non-interacting systems, it turns out that for all these gerbs thing that you consider, there's actually a very simple formula in terms of integrals of Chern-Simons forms that you can write down. And all of these things survive interactions. So if your system has some kind of a non-interacting free fermion limit, then you can extract all these interesting invariants from gerbs, this higher Berry phases and so on, but just by using free fermion models by evaluating the Chern-Simons 3 form. That's one of our results. So we can generalize this to arbitrary dimensions. The topological invariant obtained by integrating over some higher dimensional sphere with appropriate momenta are some appropriate higher Chern numbers for some non-abelian Berry connections. On the other hand, if we want to consider the higher Berry phase for any arbitrary spatial dimension, it's the integral of some appropriate Chern-Simons form. And this, for example, for 1 + 1 dimensions, the second Chern number, the invariant you get is exactly what you get from something called the duadic-Dixmuir class for Chers. The result matches, but the way to get it is much simpler. We can reproduce all of this using field theory. So the theory at the origin are two flavors of Dirac fermions. And we can do this process of computing the number of relevant deformations. So if you look at exactly our model, you get something called a triplet mass, which are 3. So it looks like this is fine. Like, you have to tune 3 parameters to close the gap. But then it's very well known that for 2 flavors of fermions, there's also something called a singlet mass. So it seems like I was expecting 3 relevant deformations, but I got 4. But for a technical reason, the singlet and triplet masses commute. They're actually not independent. So if you look at the independent masses, they're actually precisely 3. And if you add the singlet mass, something interesting happens, which is the gapless point at the origin blows up and you get a Chern insulator. It's just a thing that happens. Okay, so boundary, the edge modes. So for this model, edge modes continue to appear. They appear along this line in the space diagram. So you get edge modes by tuning 2 parameters. However, if you introduce a chemical potential, the gapless point at the origin blows up and you get a metallic phase once again. But curiously enough, instead of the edge modes separating like before, the edge modes actually become absolutely stable. So this is the point for 0 chemical potential, but for finite chemical potential, you get a metal. But the edge modes actually become more stable and you get this crown of edge modes that require absolutely no tuning. So if you are an experimentalist doing experiment at this point in the phase diagram, you'll find edge modes precisely of the form that you get in the quantum spin Hall effect. For example, the edge content is exactly the same. But this is completely in the trivial phase. And this is appearing from a different phenomenon. It's nothing to do with an SPT phase. It's appearing from the fact that somehow the system has non-contractible spheres. Okay, so that was the end of my talk. So yeah, phases of matter have non-trivial shapes. This explains the presence of terminating transitions, which is why I was interested. They can be exposed using topological textures by computing higher Berry phases. For free fermion systems, these higher Berry phases can be obtained as integrals of some appropriate Chern-Simons forms. And this produces some unusual forms of edge modes in all kinds of dimensions. So in higher dimensions, okay, so these are some outstanding questions that I would like to know the answers to. So in 1 dimension, I said that this is actually an experimentally measurable quantity, polarization. I'm not sure what the higher Berry phases correspond to, what measurable it corresponds to, what observable one can measure in lieu of doing this calculation on a piece of paper. Also, as was being asked, like this is really the most boring phase. We know of what non-contractible loops and so on look like in symmetry breaking phases, topologically ordered systems, and so on. So we know examples of this. What is missing is this Kitaev's magical recipe of how to guess the answer in every dimension using lower dimensional data. That is missing. We don't know what the equivalent of that is. But example by example, one knows, and there are many tricks like dualities and things like that, where we can take non-contractible loops and non-interacting models and then dualize this to get some interesting result for symmetry breaking, topological orders. So some of the things that we're looking at are, you can reinterpret like non-trivial topology of parameterized family of states. You can have various applications like interpret this as non-trivial topology of vacuum manifolds for symmetry breaking phases. That's one example. And if you introduce spatial inhomogeneities of a non-trivial topology, do you get something new? Turns out you do. Yeah, so with that, I'll end my talk, and if you have any questions, I'm happy. Circle, yeah. Indeed. I wouldn't call it the complex plane. Maybe you can, but yeah. It's the 2-dimensional plane of the 2 independent mass terms. Yeah, so the dimensions of the relevant parameters in higher dimensions is 3. You need if you look at an appropriate 3-dimensional space, you'll find. That sounds right. Yeah, thank you. I think that's about right. These are related to the higher 4D quantum Hall effect and 6D quantum Hall effect and so on. So the responses should be exactly what appears there.
Very elementary question. I have the impression in your constructions, the number of parameters has to match the spatial dimension. Is it always the case, or because it seems that the first example you had a one-dimensional Breuer zone and psi was sort of a cyclic variable, and then
Just this example, but yeah, the observation is correct, but it's not necessary. For example, in one spatial dimensions, there's also non-contractible three spheres, which are not shown here.
so in your omega spectrum, you introduced this sequence of iterated loop spaces. D, should I regard it as the number of parameters or the
Spatial dimension.
spatial dimension? And the number of parameters is arbitrary, or?
So it's number of parameters is infinite in principle. This ID is like the space of infinite dimensional space of infinite coupling constants.
Uh-huh.
So it's
Okay.
telling you whether there exists non-trivial wrappings of spheres and things like that.
Okay. That's and this can be given a sort of solid mathematical formulation, because dealing with the topology of infinite dimensional manifold is by no means an easy exercise in mathematics, but you.
I don't have anything intelligent to say about that. The claim is that this works.
Okay.
By experience and so on, it works.
And when you're truncating to finite number of parameters, you can still, the claim is that you can still show the full topology of this infinite
Yes,
manifold. Okay.
it is. It's the space of all possible invertible states. That's infinite dimension. You can map finite dimensional spheres onto infinite dimensional spaces. Yes. Yes. True. No, so if the space of Hamiltonians within a single phase is infinite dimensional, each of its ground states belongs to this space. Yes, that's one way. I must say, like, the formulation is not mine, but the exploiting of the results is mine. So I stuck to 3 dimensions in parameter space. It's not my mathematical achievement. So I would share their concern.
Any other questions? If not, we thank Abhishek again. A wonderful talk.